Good afternoon, this is Schweitzer, and we're going to do a little answer video here for our workbook page on titrations, particulate drawings via titrations. Okay, so let's start out here with our first option here, first question. We have a beaker here. How many moles of HCl were added to the H beaker? So I have this beaker that's kind of like my stock beaker. That's a whole bunch, but I'm not adding all of it to here. I'm just going to add enough to this guy to each equivalence point. And it's saying that that's 10 milliliters of 0.1 molar. So 10 milliliters of 0.1 molar, 0.1 molar, okay, is dumped into the beaker of 10 milliliters of this guy. So as I'm going through, I'm going to be filling out this table. Keep in mind the table is not a substitute for work. If you just put the table down and no work, you're not going to get any credit for it. This is something that I kind of made up, and other people are not going to know what you're talking about. So the known is 0.1. I like to write A above here, B above here, just to remind myself. Acid, okay. I've added 10 milliliters of this thing, 10 milliliters, which is 0.01 liters. And of course I have 10 milliliters of this guy. This is what I want to find. And this is 0.01 liters as well, so 10 milliliters. All right, how many moles of HCl were added to the beaker? That's this value right here. Well, molarity, let's do it right here. Molarity equals moles per liter. So I multiply both sides by liters, I get molarity times liters equals moles. Now, for the rest of this part of this video, I'm just going to use this formula to calculate moles. I'm not going to talk about that again. Okay. So molarity is 0.1 times the volume of 10 milliliters. Okay, we don't want to use milliliters. Back that up, and let's do 0.1 times 0.01 liters. That's a common mistake. 0.001 moles. All right, so this is 0.001 moles, 0.001 moles. How many moles of NaOH were added to the beaker for neutralization? All right, so how many were in here? I just put the answer in there already, but keep in mind we're using this equation, HCl plus NaOH produces NaCl plus H2O. And they're reacting in a 1:1 ratio. Therefore, if I add whatever of these I add, I get one of those. It's 1:1 ratio. Since I got 4 of these guys, I must have added 4 H plus ions, HCl's, and I must have had 4 hydroxides here to begin with. So that's coming up here in a moment here. But because it's a 1:1 ratio, this answer here is still just 0.001 at a 1:1 ratio produces 0.001. The moles we added equal the moles that were there before. And the next question is, what is the original concentration? So take my original moles. I'm just going to draw these in here right away, just so I want to. So OH negative, OH negative, OH negative, and OH negative. There's 4 of them. How did I get 4? Because there's 4 water produced. So I must have added 4 of those guys in the process. And there should be 4 chlorides floating around as well. Well, never mind. Those are there afterwards. So either way, the original moles is 0.001 divided by 0.01, and we get 0.1. So this guy is 0.1, and they're the same concentration. They should not be surprised because we have the same number of moles and the same amount of volume. So we want to start by looking at this volume a little bit closer when we're doing these problems to see if we can get a little bit of an insight as to what the answer might be. Okay. If the volume's the same, concentration must also be the same because we're titrating to equivalents. I drew my beakers there. Okay. Now these would be cations. There's 4 hydroxygen beforehand. There's 4 cations before we get started here. And I dump them together and I get 4 waters. And of course I would have also 4 spectator ions. Cation, anion, cation, anion, cation, anion. What are those ions? They're NaCl's. All right, let's go to our next one. All right, so it looks like I have a 0.2 molar HF solution. And a lot of times I just sketch this out. You should be trying these out. Pause the video or try it out before I do it here. It's the only part that really makes it work for you. So in this case, the known is my acid and my unknown is my base. So the known, what's known about it isn't the identity, it's the concentration. And then the volume is 0.012 liters. And then the unknown has a volume of 10 milliliters, 0.10 liters. Now you know they're not the same volume, so they're not the same concentration, but they're not that far off either. Okay. So another thing you might notice is that we'll have the same number of moles. So the same number of moles in a smaller volume means that this concentration right here is slightly larger than this one. And that's a really important idea, overall writing concept. Anybody can run the math, but that's something you want to be realizing in the background. The beakers above are mixed, causing a system to be at equivalence point. Complete the known unknown table. Okay, so let's do that. Solving out for the moles here. So I'm using my pre-established formula for moles is 0.2 is my concentration, multiply times by the volume, and I'm going to get the moles. Okay, and this is times 0.1.012, and in this case, 0.2 times 0.012 equals 0.0024. 0.0024. So this is 0.0024. 0.0024. Take the original moles, divide by the original volume, gives my original concentration. 0.0024 divided by 0.1 equals, and this should be 10 milliliters, so it's 0.01. Glad to catch that little guy. All right, so divide by 0.01 and we get 0.24. That would have been a pretty easy mistake to catch if you understood that these concentrations are fairly similar. Okay, if you didn't catch that mistake, you would have gotten 0.024. Okay, and actually you would have gotten 2.4. So way bigger, 10 times bigger. So that may have been an indication that these things are not right. Okay, they're fairly similar in concentration. Draw the appropriate particles in the drawings. Okay, so I'm adding 4 of these guys, and let's write out our equation here. So it's happening, so we know what's going on here, and how many we're going to draw. So I got HF. I'm going to use the net ionic equation. So in this case, OH negative plus yields. So we got water molecules, right? Because this guy's going to donate an H to that guy, and we're going to have an F negative left over. And I'm not showing the cations; they're there. Initial stoic ratio end. I have 4 of these. I'm going to require 4 of those in my initial beaker to match them. Minus 4, minus 4, plus 4, plus 4. And that's just what I'm going to draw. So initially I need 4 of those, so I'm going to go OH negative, OH negative, OH negative, OH H negative, and I'm going to just sketch in my 4 cations. And then run it through, I get 4 waters. Okay, let's do that. H2O, 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 and I'm going to draw my 4 anions. I'm just going to draw those as, let's do a little key here, negative equals F negative, and the positive equals Na plus. And I would get 1, 2, 3, 4 cations, 1, 2, 3, 4 anions. That's as complete a beaker as you can get. All right. Next, fill in the blanks. Phenolphthalein is a common indicator used to indicate changes in pH. So that this indicator, all indicators, should probably be neutral, right? I mean, we wouldn't want to use an indicator that itself was acidic or basic, because that would throw off everything. Phenolphthalein is, okay, if you're watching some of the lab videos and doing this in class, if you're in class, that'd be great. Phenolphthalein is clear in acids and pink in bases. Really cool little pink color. All right, next one. All right, so this is a good practice question. See if how far you're coming along here. I like to fill in my table as I'm reading through things. An unknown base is titrated with a known 0.05 molar HCl. So this is my acid, and it's known because we know the concentration, 0.05. The known is placed in a burette and is used to dispense. The student records the start of the burette to be 5 milliliters. This is another very common little table that we used in lab, and you should also be using it. The burette is, of course, used to dispense the known into the unknown, but we don't want to use all of it. We don't want to use what we pour in the burette. We want to use the amount that we dispense from the burette, and that's this guy right here. End or change. This guy is just going to be that guy right there. All right, the volume of the known starts at 5. And after adding 2 drops of indicator, it turns pink because the unknown is a base. So this guy originally, 15 milliliters unknowns placed in the beaker. So that's 0.015 liters, okay? And this, of course, turned pink in the bottom beaker. They titrate until it turns clear, and the burette read 15. Change here is 10 milliliters. That goes here, 0.01 liters. All right, so solve it out for the moles. All right, let's do that. 0.05 times 0.01 equals 0.05 times 0.01 is 0.0005. And of course, at that point, we're at the equivalents, and these are equal. 0.0005. Divide the two out to get the original moles, divided by the original concentration, divided by 0.015 equals 0.033. All right, 0.033. Okay, so it looks like, does this answer make sense? Well, I have the same moles in a larger volume, so it should be less concentrated. In fact, looks like there's about 10 to 15, so it should be about a third less. Okay, I think that number makes sense. Next one. All right, 10. Now, this next couple problems here you're not able to solve for the actual concentration because we don't know any concentrations in 7 and 8. So all I know is what's the relationship between them. So 10 milliliters is added to 10 milliliters equivalents. What can you postulate? Sounds fancy. Postulate about the concentration of the HCl versus NaOH. Well, you could fill out a known unknown table. And of course, you have a volume at the bottom. And if they're both 10 milliliters at the bottom, and the moles are the same, then the molarities would also have to be the same. Now, I don't know what that is, but they are the same. And therefore, these two are equal. And you should have been aware of that. All right. Now, in this case, again, known, unknown. Getting a little sloppy here. This pen's slowing down. Sorry about that. Molarity, moles, liters. Now, again, go through the whole thing, but with the same number of moles in this guy here, same number of moles, and a larger volume makes this less concentrated, makes this more concentrated. All right. Here we have a little video. Looks like a surprise little guy here. You should have already looked at that and watched it. Okay, it's not very long. Go through and solve it out on your own. Here's the stuff they gave us for this thing. So we have 5.2 milliliters. So the known is 0.15. The unknown, I didn't write down the volume of it. That's a stinker. All right. All right. So this guy here is going to be 5.2 milliliters. So this is point. All right. So 0.0052, and then I'm going to solve for my moles. All right. And in this case, let's go ahead and do that. So it's going to be 0.15 times 0.0052. And let's get our moles here. 0.15 times 0.0052, and we get 0.00078. All right. 0.00078 equals 0.0078 original moles divided by original volume. Let's flip over and just check out what that original volume was. And it was 15 milliliters. All right, so that's the original guy there. And there we go. All right, the base was 15 milliliters. 0.015 liters, divide them out. Now notice that this guy is 3 times that guy, so it's 3 times the volume. So without doing the math, we have the same number of moles and 3 times the volume. Therefore, what do you think that is? So divided by 0.015, of course, awfully close to 0.052. Does that make sense? It's the same number of moles and 3 times the volume, so it's 3 times less concentrated. And I hope that's working out well for you. Thank you very much.